Hi, let's see if I can solve problem 5. I have prepared somewhat. Lemma 1 gives the value of the j function for the 2 of exact order 4, and not the values, but an information on the value that modulo 2 plus 2 times the imaginary unit, it's equivalent, j44 is equivalent to 2 plus chi2 of 2, and j of chi2 point chi4 always is equivalent to minus 1 modulo 2 plus 2i. And I will actually compute the j of this one as well. And I've prepared a computer program for doing it, because the last two here, that's rather intractable. So I'll try to do these two by hand and then check with the Maple program I've made. So we start with q equals 5. And 2 is a generator. So chi4, we maps it to the imaginary unit. The square goes to minus 1, and this to minus I. This, of course, to unity itself, and naught, by definition, goes to naught. So that's x4 of chi4 of x. And chi2 of x so maybe we should make a table with the same ones. 1 minus x, one minus 2, it's minus 1, that equals 4, 3, 2. So we're just going backwards, of course. Then chi4 of 1 minus x. And that's all we need. Four gives minus 1, 3 gives minus I, and 2i. So let's go. Naught times 1, 1 times naught vanishes. Then it's minus I minus I squared minus I we are in the case where it should be equivalent to 1 modulo 2 plus 2i, so we just add that once, so it's very simple. So that seems to be right. So that's, we take that one together with that one, naught, naught, unity, I, and the imaginary unit once again. And if we subtract 2 plus 2 times I, we get exactly -1. So that seems correct as well. And now let me check the Maple program I made. We start defining the Galois field, and then we must find a primitive element. And the new version of Maple actually has a way of, it's simply called primitive element of f. So it's very simple to do nowadays, but I have Maple 2020, so I need to compute it. So we just take the last one. So every time we have a primitive element, then it's assigned to prim. So when the for loop is done, prim is the last primitive element, or the largest primitive element. And just to make sure, I compute the powers of it to see that it starts with 1 is trivial, ends with 1 is trivial, but we have no repetitions other than that. The next problem is to define the logarithm so that we can compute the value of chi4. And we actually don't do that. We only take the logarithm modulo 4. So I list those. Now that is 1. So that's the primitive element itself, and then times all four powers of the primitive element. So we get number 1, 5, 9 to the 9th power, etc. And then we do the same with 2, 3, and to naught and the other powers. So if it lies in A4, then chi4 of this number, that's 1 modulo 5, should give unity. This is actually non-necessary, but there's just so we make a sequence of these sets themselves. We don't need to compute that really, but I'll let it be to check that I'm doing that the procedures are doing what I believe they will, what they're supposed to do. So here we just have a sequence of 4 of these sets, and that means we can look up the logarithm. If it's here, the logarithm is naught, modulo 4. Here it's 1 log and 2 and 3 modulo 4. And that means that if we give some element x, we first find out in where does it occur in this guy. And if it's in table 2, for instance, here, then it must be I to the first, the imaginary unit to the first, and here to naught. And then just as a safeguard, I start initializing A to 2, so that if none of this happens, then we get an error message. That's modern programming. Always checking the prerequisites the procedure has. Can't expect people to be able to follow the rules. So people may get it wrong. All right. So that was chi4. And then I just check that it's correct. Naught is mapped to naught, unity to 1, and the generator was 3 modulo 5, it's mapped to the imaginary unit, 4 to -1, 2 to... That's the opposite of what I did on the other page. Then we compute chi4, or j of chi4, point chi4. So we have to subtract here 1 minus x, and the same here. So this is chi4 squared, that's chi2, and it seems that I get the same that I already wrote, although we use different numbering. Interesting. -1 minus 2e, 1 plus 2i. No, we didn't. We got this one, and that's because I used another enumeration. I got another primitive element in the program here than I did in my own calculation. I really think this is silly because it will just give the conjugate of this guy. All right, that's the program. Next, we should do the same with q equals 9. And we have already worked on NF9, so I've taken that from problem 4. And we have chi2 here. And this is what? That must be, oh, that's psi. Yeah, so now we can, I'll just write the x values again. And we did find a generator. T was our generator. So that's T is mapped to I, and then we just take them one at a time. Minus T plus 1 is mapped to -1, minus T minus 1 to minus I, minus unity to -1, minus T to minus I, T minus 1 to, oops, I get unity here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, so that's minus I here, minus, that's not a good one. So every time we go up, we multiply by I. Minus I times I gives +1. There we go. So it's a repetition. Minus t is the imaginary unit, t minus 1, minus 1, t plus 1, minus I. All right. Now 1 minus x one minus minus 1 gives 2, that's minus 1. 1 minus t minus t minus t minus 1. Minus x, that's minus t plus 1. Yeah, that's minus 1. T plus 1. T minus 1. T minus 1. Oops, that's not good. 1 minus minus 1, that gives minus 1. And minus t minus 1 plus 1, that's just t. That's the one we don't have. Minus t plus 1, that's minus 1. Minus t, that's the imaginary unit. Minus t minus 1, minus t plus 1 minus 1. T I natural, it was the generator. T minus 1 minus 1. So the product. One minus I plus, that gives plus 1 plus I minus I 1, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We're just plus square root minus 1 equals 2. They cancel, it's just 2. That wasn't very nice. Well, let's do kite 2 as well. So that's just squaring this guy up here, x4 of x. Naught, naught, unity, unity, minus I, unity, plus I, plus 1, 1, 2, 3, 4, plus minus 1 imaginary I, that's no good. So something is wrong here. Let's try to do it on Mabel and see what happens. So 2t plus 1. We come through all of them. 2t plus 1 plus 2. Yes. So that's a generator, all right. And it doesn't necessarily fit with what I did, so I can't really control it. Maybe I should require the polynomial I used to get this. I really forget what it was, so let's just see if I can find that. Then I'm not sure that I can find the right element. Well, let's try. Nah. Let's check what it gives, by the way, first. Two mapped to unity. Did I get that? 2 mapped to unity, yes. In this case, I believe it should give 3. It should be equal to 3 modulo 2 plus 2i, and that's what it gives. Chi 2, chi 4, should be equivalent to minus 1 modulo 2i plus I. No, that's true, it's 4. If we add 1, it's 4. And that's, of course, 2 plus 2i times 1 minus I. Should be 4. So I believe what Mabel is doing is correct. So they both give 3. And neither of mine did. They are not too far off. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. That's not very good. So let's just check again. Two, 4, 1, 1, minus I, plus 1, plus I, plus 1. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right. But then we miss one down here. One minus I plus 1 plus I minus I minus I plus I. So we like 1 minus I. This doesn't really help. So it's difficult doing it by hand, we can conclude. They say it helps with a horizontal line, but one should not use, oh my God, one should not use vertical lines. All right, so I wasn't able to do it by hand on the tablet, but it seems that the Maple program worked. So that was, the next one is 13. And of course they are conjugate, and chi4, j of chi4, chi4. Now it's 13, that's 5 modulo 8. So it should be equal to unity modulo 2I plus I. That's what it is. And the other one, now adding 2 plus 2I gives minus 1. And that's what it should give. So that seems to be it. And finally, 17. You see, this is quite a lot of work, but it doesn't take very long. And when it works, then it's easy to get a lot of results. We see the modulo of it is square root 17. I didn't check that with the other ones. And let's just check what the square root was when we had 13. The square root is, the norm is square root 13, as it should be. Very good. So I'm sure we are right here. Now it should be equivalent to 3, so we just subtract 4i and 4, that was minus 5, and then add 4, or add 8, so we get 3. And this one, when we add 4i, it becomes minus 1, as it should. So the best way to solve this problem is to make the example with 5. Q equals 5. Then make a Maple program or whatever language you use. And then just check that you get the right result. There's only one result really using lemma 1. So it's easy to check that we've done it right. And I wasn't able to do it right by hand, so this was wrong. And I don't really care much where the fault is. If I had it on paper, I could compare with use Maple to make the tables, and then I could see where the mistake occurred. But who cares?